Thank you for introduction. And I'd like to thank the organizers for giving me this opportunity to talk here. And today I will talk about the possibilities of using quantum annealers or quantum computers to detect the quantum dynamics quantum many-body localization in quantum system. Yes. And first I'll explain our aim, the aim of this work, and introduce some related works. And then I'll explain the models and the methods of this work. And then I'll show some results about the time of relation based on exact diagonalization. And finally, I will give some summary. First, the many-body localization is an extended concept of the Anderson localization. And the Hamiltonian of the Anderson localization is given as shown here. It consists of the hopping term and disorder term. And so there is no interaction between the quantum particles, only one particle system. If there is only the hopping term, then the quantum particle in the lattice shows spreading behavior, but when the disorder is strong, then the wave function localizes like this. In contrast, the many-body localization occurs in many-body quantum system, so there are interactions. And so we can say the many-body localization is the localization in a many-body quantum system with large disorder. Now, let me explain the motivation of this work. First, the numerical studies of many-body localization, MBL, often suffer from finite size effects. If we could use a large-scale quantum computer, maybe we could investigate true many-body localization, hopefully. But current quantum devices are too noisy to compute the exact eigenstates. And then the quantum dynamics actually can be used to detect many-body localization. In fact, the memory effect, which is the robust against noise, characterizes localization. And actually, there are some experimental works on many-body localization using quantum devices. And for example, quantum annealer, trapped ion quantum computer, and quantum superconducting qubits, and so on. Now, there are many diagnostics of MBL. First ones are based on highly excited eigenstates. For example, level statistics shows Wigner distribution in the thermal phase, and it shows it is Poisson distribution in the localized phase. This figure shows the level spacing ratio depending on the disorder strength. This upper dashed line corresponds to GOE, and the lower one corresponds to Poisson distribution. And next, the entanglement entropy shows the volume law in the thermal phase and area law in the localized phase. The second one is based on quantum dynamics. There are some quantities, for example, invariance, or actually the probability density, and magnetization, and the entanglement spreading, and so on. This figure shows the time evolution of probability density. This corresponds to the thermal phase, and this corresponds to the localized phase. But it is controversial whether there is a true many-body localization phase. Before the mid-2010s, the many-body localization transition was considered a continuous transition. Actually, the numerical and the experimental results support the MBL transition. But after the late 2010s, it was found that the transition point found here was actually localized for a long time in the pre-thermal regime, like here. And it is impossible to detect the true many-body localization point here, numerically or experimentally, because the system size is too small to detect this transition point. And in this study, we focus on the localization in the pre-thermal MBL regime. So we will see the crossover from the thermal regime to the pre-thermal MBL regime. Now, this work was inspired by experiments using quantum annealer. The references here. In this experiment, they used the reverse annealing protocol with a mid-anneal pulse. The initial state was all spins up or all spins down. And after the quench protocol, the measurement provides the magnetization. And this figure shows the average magnetization as the function of the disorder strength. Actually, this axis corresponds to the disorder strength. The result shows that the system is thermal in the weak disorder regime and localized for strong disorder. Because in the thermal phase, the magnetization is almost zero, and in the localized phase, the magnetization is plus minus L. L is the system size, so the initial state was maintained, so it shows the memory effect. Now let me introduce the models and methods in my work. Actually, this work is completely carried by using the classical computer, so it's just numerical simulations in the ideal system. The Hamiltonian of this model is given like here. It is just the transverse field is in model chain, one-dimensional chain. The L is the system size, and the local fields are given as the uniform random numbers, and the interaction J, and the transverse fields are given as 1 plus random numbers. And here the W is the disorder strength, and sigma here is means the static noise strength. It's just a random number. And we focus on the two observables. One is the magnetization in the z direction. And the second one is the twist overlap, given as shown here, and new twist is the twist operator, and which is defined as shown here. They are easily obtained through the measurement of each qubit in quantum devices. That's the point. Let me elaborate on the twist overlap here. The twist overlap with the eigenstates size eigenstate in this case, can be detected can detect the MDL transition. And the twist overlap is almost zero in the thermal phase. And because the twist operator causes spin wave-like excitation, and so the U-twist side is orthogonal to the original eigenstates. But such a long wavelength perturbation gives little effects on eigenstates in the localized phase. So in the localized phase, the twist overlap has finite value. Now, this slide shows the quantities varied using eigenstates. The left panel shows the entanglement entropy, the average, and the standard deviation. The entanglement entropy is large in the small disorder region and decays to zero in the localized phase. And it shows a peak around here. And the twist overlap is almost zero in the weak disorder region. It's in the thermal phase and increases with disorder, and both the average and the standard deviation increases. Now, let's move on to the time aberration based on the exact diagonalization. The solution of the Schrödinger equation is given as shown here. Here, psi naught is the initial state, and the phi k is the eigenstates, and the ek is the eigenenergy. So we can get the exact time aberration using the exact diagonalization of this Hamiltonian, of the Hamiltonian. And the setup is like here. The initial state is all spin-up state, and the magnetization and the twist overlap are evaluated using the wave function at the final time. And here we set the final time is 10. And this shows the system size dependence of magnetization, but it's actually the dependence on the disorder strengths for different system sizes. It shows the increasing behavior. In the weak disorder region, the magnetization is almost zero. And the large disorder region, the magnetization is almost the system size. It is the value for the initial state, so it shows the memory effect as expected. And this shows the system size dependence on the twist overlap. This is based on the quantum dynamics, but these look very similar to the ones evaluated using eigenstates here. So these are based on the quantum dynamics, and these are based on the eigenstates. So they look very similar. That's the point. Only the difference is like here, the curve is a bit different. Now, this slide shows the noise dependence. Actually, the static noise is in the interaction and the transverse field, but the static noise dependence look negligible, like here. Now let's move on to the time evolution of magnetization. This figure is in the small disorder region. So the magnetization decays to zero because it's in the thermal phase. In the middle disorder region, the figure B shows that the fluctuation around some finite values, like this. And in the large disorder region, the figure C, the magnetization fluctuates around the initial value here. It corresponds to the memory effect. Now let's move on to the twist overlap. In the small disorder region, the twist overlap rapidly decays to zero because it's in thermal phase. And in the middle disorder region, it decays rapidly, but we can see small fluctuation after the decay. And in the large disorder region, it's very different from the magnetization. Some samples oscillate around the initial value 1, but others oscillate like this with large amplitude. So this causes the large variance in the average of the large variance in the twist overlap in the large disorder region. Now, this slide shows the noise effect on the time dependence. Actually, the static noise affects the time evolution because these two look different, but the details of the time evolutions are averaged out in the disorder dependence because we only see the values at the average of the at the final time here and here. So these look almost same. But in contrast, the time dependence of the twist overlap are very similar between the noiseless and the noisy case. Now, let me summarize my talk. The localization in a disorder spin chain is detected by evaluating the magnetization and twist overlap after time evaluation for many disorder realizations. The magnetization and twist overlap can be easily obtained from the measurement of qubits in a quantum device. And the next one, the twist overlap can be a promising probe for detecting many-body localization in quantum computing approaches because the twist overlap evaluated using wave function after time evaluation behaves similarly to that calculated using eigenstates under the condition in this work. Thank you for your attention.
Do we have questions?
So thank you for the nice talk. I have a question related to the computation of the twist overlap. So you mentioned that you performed the calculation considering eigenstates in the middle of the spectrum. Did you analyze what happens when you move away from the middle of the spectrum? For example, if you take into account the ground state, do you see any signal also there? Is there evidence of a transition or a crossover?
Yeah, actually, I haven't tried different region of the spectrum. Actually, these are evaluated using the middle energy spectra, but actually the edges of the energy spectra, it usually shows the only localized behavior. So usually we use the middle of the energy spectrum for these studies.
Okay, thank you.
Question in the very back.
Can this analysis distinguish between the Anderson localization and many-body localization?
It is actually the Anderson localization and the manifold localization are different systems because there are interactions in the manifold localization, but in Anderson localization occurs in a single particle system. So if we weaken the interactions in this system, maybe we can see some kind of the crossover from the Anderson localization and manifold localization.
Okay, thank you.
Great. Is there any more? Oh, we have a question, please.
It's not clear to me how this overlap with text localization, because as you were saying, now the question is whether this pre-thermal regime is obeying the eigenstate normalization hypothesis or not, but I think that this overlap, also in the presence of subdiffusion in a thermal system, would present a similar signature, while the time and entropy instead really discriminates between these subdiffusing super slow regimes or not. So why did you go to these very small times? Because at this point you cannot distinguish any subdiffusion from relocalization. And do you think that this can be actually done in simulators? Because localization in the end is a question about infinite time dynamics, so you need infinitely long coherence times.
Yeah, our purpose is to detect localization using quantum computers or annealer easily, so we want to test the dynamics in a short time, because if it's in long time, the coherence, because of the coherence time, we cannot distinguish the localized or some phase. So the point is, for a short time, we can distinguish some characteristics in the localized and some phase.
The point is that the difficulty is exactly going with long times. Everybody agrees that the short times the dynamics freezes. The point is whether this unlocks or not quaternal phase in the long time regime. So what are you answering that is not already known from all the other rules? What is their view when this was already known?
Sorry, what is
We can talk later.
I think if we can take the discussion offline, that will be good. Okay, let's thank the speaker again.